One of the series that you might already be familiar with is the geometric series. A geometric series comes from a sequence where the ratio between consecutive terms is the same. Notice how that in the formula that we have here, n, my variable is in the exponent, so my variable n is in the exponent, and the starting value for n is 0. But generally, the starting value doesn't have to be 0, by the way, so it can start at any value of n. So this series is going to converge when the ratio r, the absolute value of r, is less than 1. And in that case, all these numbers are gonna add up to a over 1 minus r. So you may think of this formula as this a being just the first term. This is the first term. And the r here, this is the ratio. So let's take a look at the example that we have down here. We have seen this guy already. This is just the sum of 1 over 2 to the n, where my n goes from 0 to infinity. Now, well, if I want to write it in the forms that we have here, let's see, my a is just going to be the first term, so this guy is going to be just the sum of 1 times 1 over 2 to the n. I mean, I can write of this as 1 over 2 to the n, when my n goes from 0 and it goes all the way to infinity. So from the formula, this sum is just going to equal to 1 over 1 minus 1 over 2. So 1 minus 1 over 2 is a half, and I flip that, I bring the 2 to the numerator, so this guy is just 2. So that means this series converges to 2. Notice how I can also view this formula as being just the first term divided by the ratio. So here, my 1, this is the first term that we see here. And the ratio, notice how the ratio between from term to term is just going to be 1/2. So that means my ratio that we have down here is just 1/2. So it's a over 1 plus r, where a is the first term and then r is the ratio. Another way that you can think of this formula, or another way that you can add up all these numbers from geometric series, is that you can do this. I can give this series a name, so I let all these sums to be just some values a. So this is going to be 1/8, 1/16, and so on. So I let all this sum add up to a number a. Now then, I can multiply a by something. In this case, I'm going to multiply a by 2, which is the reciprocal of the ratio that we have here. So now my 2a is going to be, let's see, let me kind of move this a little bit to the side. If I multiply all this number by 2, I'm gonna get 2 plus 1 plus 1/2 plus 1/4 plus 1/8, and so on. Notice how I just multiply all the numbers that you see on the top by 2, and I get the numbers at the bottom. Now, if I realign this a little bit, so let me shift this 1 unit to the left. Notice how the numbers actually match, so I see the same numbers here. So that means I can subtract the top equation from my bottom equation, and if I do that, I subtract a from 2a, so I'm just gonna get only a on my left hand side. And from the right hand side, the 1 and 1 here is going to get cancelled out. 1/2 and 1/2 is going to get cancelled out. So all these numbers are going to get cancelled out. So once again, I subtract the top equation from my bottom equation. So the only thing that is left on the right hand side is going to be just the number 2. So that means a is 2, which means the sum of all these numbers are just going to be 2, which is the same thing that we have seen earlier. So let's take a look at the next one. Notice how if we write up all these numbers, they are just going to be 1 plus 3 plus 9 plus 27 plus 81 and so on. Now then, let me show you the wrong way to do this for a moment. Well, one wrong way to do this is just, well, let me just use the formula. So it's going to be the first term, which is 1. divided by 1 minus the ratio, and the ratio in this case is just going to be number 3. So now then, if I divide 1 by 1 minus 3, which is negative 2, I'm going to get negative 1/2, which looks kind of weird because if you add all these numbers up, how are we going to get 1/2? And this is because this is not correct. This formula only works when the ratio r, the absolute value of r, has to be less than 1. In this case, because my r is 3, so the absolute value of this guy is greater than 1. So then that means I can now conclude that this guy is going to diverge. And that makes sense, right? Because all the numbers that we're going to be seeing here it's only going to get larger and larger if we add all these numbers up. So that should give me infinity. That should give me something really, really large. So for part B, this series is going to diverge. So let's take a look at part C here. I have 9 over 10 to the n. So if I were to write all these numbers out, it's going to be 9 over 10 to the 1, which is 9 over 10, plus 9 over 10 squared, which is 9 over 100, plus 9 over 1,000, 9 over 10,000, and so on. Notice how in the summation here, the value of n actually start off with 1 now, but this is okay. I can just use the formula a over 1 plus r by seeing a as being just the first term, and then my r is going to be the ratio. So my first term, the first term that we see is going to be 9/10, and then the ratio is going to be just 1/10. So this sum, notice how the ratio 9/10, the absolute value of 9/10 is less than 1. So that means this guy is going to converge. The ratio is 1/10. So because the absolute value of 1/10 is less than 1, so that means this guy is going to converge, and I can use the formula. So this sum is going to equal to just the first term, which is 9/10, divided by 1 minus the ratio, and my ratio is going to be 1/10. So this is my ratio. Now then, if I compute this guy, this is going to be 9/10 over 9/10, and that is going to equal to 1. In fact, if you look at this sum carefully, the sum that you are looking at, let me kind of write this on the side. The sum that you are looking at here, this is actually 0.9 plus 0.09 plus 0.009 plus 0.0009. So this guy is actually just 0.9999 and so on, or 0.9, and then I'm going to have the repeating 9 here. So this guy, well, we can kind of see this is going to just equal to 1, as we can see here. So this guy converges to 1. Let's take a look at the next example. I have negative 1 to the n, where n goes from 1 to infinity. Now then, this sum is going to be negative 1 to the 1, which is just negative 1 plus 1, plus negative 1 again, and then plus 1 again, and negative 1 again, and so on. Notice how this is also a geometric series, where my ratio, the value of my r, is going to be negative 1. Now, because the absolute value of this guy is equal to 1, so then that means I cannot use this formula. This formula only works when the absolute value of my r is less than 1. So that means this guy now diverges. Now, some of you may ask, by the way, why can't we just say that the negative 1 and 1, they get cancelled out? So let me try to do this. Let me kind of copy and paste this. So let me do it on the side here. Now some of you may ask, well, if I put a parenthesis like this, it seems like negative 1 and 1 is going to get cancelled out, so we should get a 0. Do we not? Well, if we actually put a parenthesis the other way, so let's say, if I actually put parenthesis this way, so the 1 and negative 1 here is going to cancel out, yes. And the 1 and negative 1 here is going to cancel out, and so on. it will turn out that everything after the negative 1 that we see, the first term, is going to get cancelled out. So I'm going to be left with only negative 1. So by the same reasoning that it should equal to 0, it also should equal to negative 1. So to deal with this problem, we're just going to say that it diverges, and it actually kind of coincides with the formula that we have up here as well. We have a few more examples in the next page, so let's take a look at that. The part E that we are looking at here, at first glance, this one doesn't seem like a geometric series. So let's try to simplify the terms in the summation a little bit. If we look at this guy, I have, let's see, 5 to the n times 3 to the 1 minus 2n. Well, this guy is just the same as 5 to the n times 3 to the 1 divided by 3 to the 2n. So now, 3 to the 1 is just 3 to the n, 3 to the 2n. I can rewrite this as, 5 to the n times 3 over 3 squared to the n. Okay, so when we have nested exponent, we can simply just we can simply multiply the exponent just like what we see here. So now 3 squared is 9, so this is going to equal to, 5 to the n times 3 over 9 to the n. And this is just the same as 3 times, 5 over 9 to the n. So it turns out that the sum that we are looking at here, this is just the same as the sum of 3 times 5 over 9 to the n, where my n go from 0 all the way to infinity. Now we can kind of see that the first term is just going to be, first term is just going to be 3 times 5 over 9 to the 0, so it's just going to equal to to 3, and the ratio is just going to be 5 over 9, and the absolute value of 5 over 9 is less than 1, so this guy is going to converge, and its value is going to be just 3 divided by 1 over ratio. So this is going to equal to, 3 over 4 over 9. And that is going to equal to 27 over 4. So that means this guy is going to converge to 27 over 4. Okay, so let's move on to the last one. Here I have the sum of n over 2 to the n. Now if I were to write out the numbers in this series, this is going to be, when n equal to 1, it is going to be 1 over 2 to the 1, 1 over 2 to the 1, plus 2 over 2 to the 2, plus 3 over 3, 2 to the 3, 2 to the 3, and then 4 over 2 to the 4, 5 over 2 to the 5th, and so on. At first glance, once again, this doesn't seem like a geometric series. However, there is some trick that we can use to find the sum of this term. So, notice how the ratio here is 1/2. So I'm gonna let a equal to this thing. So let's say I'm just gonna let a variable a equal to just this whole guy. And as I said earlier, the ratio between these numbers seems to be 1/2, but the numerator seems to increase from 1 from term to term. So I'm just going to multiply all the terms in this summation, all the terms in this series by 2. So if I multiply everything by 2, I'm gonna get 2a is going to equal to, 1 over 2 to the 1, which is 1/2, times 2 is gonna be just 1 plus 2 over 2 to the 1 plus 3 over 2 to the 2 plus 4 over 2 cube plus 5 over 2 to the 4th. So here once again I multiply both sides of my top equation by 2. So the 2 kind of get cancelled out. So from 3 over 3 to the 3, I'm only going to get 3 over 2 square now, because one of the 2 get cancelled out by the 2 that I get multiplied. So now notice how my terms I can kind of match the term from my first equation to the term from my second equation. So let me kind of realign this a little bit. So let me shift my things to the right. Now then, I can subtract my top equation from my bottom equation. If I do that, I subtract a from 2a, so I'm only going to get a on my left hand side. 1 minus nothing is just 1. Plus, if I subtract 1 over 2 to the 1 from 2 over 2 to the 1, I'm going to get 1 over 2 to the 1, which is just 1/2. Plus, if I subtract 2 over 2 squared from 3 over 2 squared, I'm going to get 1 over 2 squared. If I subtract 3 over 2 cubed from 4 over 2 cubed, I'm going to get 1 over 2 cubed. And so on. Now you see the pattern. Notice how my right hand side is already a geometric series where the first term is 1 and the ratio is just 1/2. So this whole sum is going to equal to the first term 1 over 1 minus the ratio, which is 1/2. And this is going to equal to 2. So that means this sum is just going to equal to 2. So now I can conclude that this guy converges to 2. So here's my answer for part of F here.